Ionic bonding and properties for GCSE, IGCSE or general chemistry.
Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on.
Here is an overview of the lesson, a review of chemical bonding, ion formation, group number and ion charge, the structure of ionic compounds, ionic empirical formulae, and the properties of ionic compounds. If you are a UK GCSE candidate, then you can check against the AQA, EdXL and OCR specifications, and you'll see that each require these subtopics, as indeed do the IGCSE specifications as well. So the first idea to review is that of metals and non-metals. We can see that metals are positioned to the left of the periodic table and non-metals are positioned to the right. So we have grey background for the metals, a beige background for the non-metals. So the two types of element, metal and non-metal, allows for three possible combinations. We could have a compound combining a metal and a non-metal, a compound combining a non-metal and a non-metal, and of course a metal and a metal. There are three types therefore of bonding: ionic, covalent and metallic. Pause the lesson, allocate the type of bonding to the element combination. Is it ionic, covalent or metallic for non-metal plus non-metal, etc.? Pause, come back to check your answer when you are ready. So to continue, metal and non-metal is of course ionic, topic of this lesson. That leaves non-metal and non-metal as covalent, and of course most obviously metal and metal as being metallic. So here are some compound names or substance names: magnesium oxide, copper, sodium bromide, sulfur dioxide, etc. Run down that list of substances and decide on the type of chemical bonding. Pause, come back, restart when you are ready to check your answers. Okay, so magnesium oxide is a metal and a non-metal, so that of course will be ionic. Copper is a metal, so that'll be metallic. Sodium bromide, well that's metal and non-metal. Sulfur dioxide, those are two non-metals, so covalent. Hydrogen chloride the same, two non-metals, and then an alloy, of course, contains metals only, so that would also be metallic. Moving on to ion formation and dot and cross diagrams. So ionic bonding is centered around the formation of ions, which come from atoms by the loss or gain of outer shell electrons. For instance, if sodium and fluorine reacts, sodium 281, 2 electrons in the first shell, 8 in the second and 1 in the third. Fluorine, 2 in the first, 7 in the second. Pause and predict the ions formed by sodium and fluorine by the loss or gain of outer shell electrons. Come back to check against my idea. To start again, we have sodium gaining 1 electron to form the sodium plus ion. Metal atoms become positively charged ions because of the loss of an electron, whereas fluorine was 2 and 7 in the outer shell is now gained an electron to form 2, 8, and is therefore negatively charged. Non-metal atoms become negatively charged ions through the gain of an electron or electrons. Ionic bonding is the strong electrostatic attractions between the oppositely charged ions that result from this electron loss and gain. Electronically, each element achieves a noble gas electron structure. Sodium was 281, has become a sodium ion 28. That is the same electron arrangement as neon. Fluorine was 27, has become a negatively charged fluoride ion with an electron arrangement the same as of neon, 28. So they achieve a noble gas electron arrangement or noble gas structure. Your teacher may refer to them as full outer shells. So ions are formed from atoms by the loss or gain of outer shell electrons to achieve a noble gas structure or electron arrangement. These electron arrangements are stable. What's significant of the noble gases is they are unreactive. Their electronic structures are stable. So here's an equation for you to complete. A sodium atom and a chlorine atom forming an ionic product. Pause, complete the equation, come back to check against mine when you are ready. Okay, so the sodium atom becomes the sodium ion by losing an electron. If you notice here, chlorine has gained an electron, so it becomes the chloride ion. So we've got sodium chloride, positive and negative ions. Here's a second equation. Pause, complete the equation with the missing information, and come back to check when you are ready. Okay, so lithium has lost an electron to become Li plus lithium 1 plus ion. Fluorine 2,7 has become the fluoride by gaining an electron, so the electron arrangement is 2, 8. So let's move beyond group 1 and group 7. Let's look at a group 2 and a group 6 compound. Complete the missing information. Come back when you are ready. To reveal, magnesium Mg becomes Mg2 plus, 282 becomes 28. It's lost 2 outer shell electrons, hence it is a 2 plus ion. Sulfur 286 has become 288, so it must be a negative ion, but a 2 negative ion. Each electron gained or lost changes the charge by 1 unit. So losing 2 electrons, magnesium becomes 2 plus. Gaining 2 electrons, sulfur becomes 2 minus. Okay, second problem, calcium and oxygen. Pause, complete the missing information, come back to check. Okay, so to reveal, the missing ion is of course a calcium 2 plus ion. 2882 has become 288. It's lost 2 electrons. Losing electrons makes the atom become a positive ion, but 2 positive, it's lost 2 electrons. Oxygen has become oxide 2-, it's gained 2 electrons, so its electron arrangement is 2-8, like that of neon. Calcium is like that electron arrangement of argon. So moving on to dot and cross diagrams, here rather than representing electrons as sets of numbers, electron arrangements as sets of numbers, we use shells drawn as circles and place dots and crosses on those circles. So we've got 2 in the first shell, 8 in the second shell, and 1 in the third. I've gone for blue crosses rather than dots. It's more normal to have dots. So 2 in the first, 7 in the second. Here's the products, sodium ion and the fluoride ion. Pause, complete the shell diagram for the product ions, please. Come back when you are ready to check. Okay, so here are the positive sodium ion and the negative fluoride ion. Sodium loses 1 outer shell electron, fluorine gains 1 outer shell electron. They become oppositely charged, so they attract each other. The positive and the negative attract. That's the ionic bonding, and they have a stable noble gas electron structure. So let's give you another problem. Magnesium and oxygen. Here are the atoms, drawn as dots and crosses for magnesium and for oxygen. Complete the ions formed. Pause, come back when you are ready. Okay, so to reveal, magnesium 2+, it's lost its 2 outer shell electrons here and here have been lost. Notice the way the dots and crosses map the identity of the electron transfer. So oxygen has gained the 2 outer shell electrons from magnesium. The 2 crosses are now in the oxygen outer shell. So Mg2+, oxygen 2-. Lost 2 electrons, 2+, gained 2 electrons, 2-. Of course, the attractions between the magnesium 2+ and the oxide 2- are strong electrostatic attractions and form the ionic bond. For clarity, and as only outer shell electrons are involved in bonding, the inner shells can be omitted from dot and cross diagrams, and this simplifies everything into an outer shell only diagram. So calcium 2,882, oxygen 2,6, going to make calcium oxide. Instead of drawing all of the shells, we just draw the outer shell, calcium with 2 electrons. It's in group 2. Oxygen, if you recall, had 6. We therefore form on the right-hand side a calcium ion, where there's 2 alternatives here. You can either draw the outer shell with no electrons and a 2+ charge, or you can move to an inner shell with 8. Most examiners prefer to see no electrons in the outer shell, although they usually allow the alternative. 2+ ion is lost 2 electrons. Oxygen, outer shell only, had 6, now has gained 2, has 8. So there we have the outer shell only electron arrangements for calcium and oxygen forming calcium oxide. Here are some problems for you. Forming sodium oxide from sodium and oxygen. Here are the atoms, sodium and oxygen. Can you draw the appropriate ions and with the correct charges on the right-hand side? Pause, come back to check your answer when you are ready. Okay, so here is my answer. 2 sodium ions, each separately at +1. Oxide ion at 2-. So oxygen has gained 2 electrons, 1 from each of the sodiums. Second problem for you. Can you draw the atoms and the ions in the formation of magnesium chloride from its atoms? Pause, complete your diagram, come back to check when you are ready. Okay, so to continue. Magnesium in group 2, 2 electrons in the outer shell. Chlorine in group 7, 7 electrons in its outer shell. Each chlorine will gain 1 electron to form the chloride. Magnesium will lose 2 electrons. We can track the identity or the location of the magnesium outer shell electrons by using dots and crosses. So this is why there is the requirement for dots and crosses. So next topic or subtopic, group number and ion charge. So if we consider potassium, that's in group 1. How many outer shell electrons does potassium have? Well, of course, it has an electron arrangement of 2, 8, 8, 1. So it's got 1 electron in its outer shell. If we think of chlorine, 2, 8, 7, of course it's got 7 electrons in its outer shell. Pause and complete the numbers of electrons in the outer shell of the remaining atoms. Come back when you are ready. Okay, so if we look at magnesium, obviously it's got 2 electrons in its outer shell. Sulfur has got 6. Sodium has got 1. Bromine has got 7. Oxygen has got 6. Calcium has got 2. So I'm hoping you'll see there's a relationship between the group number and the numbers of electrons in the outer shell. Group 7, 7 in the outer shell. Sulfur, group 6, 6 in the outer shell. Oxygen, group 6, 6 in the outer shell. Calcium, group 2, 2 in the outer shell. Could you decide, therefore, on the charge on the ion formed? So these are the numbers of electrons in the outer shell of the atom. What would be the charge on the ion formed? Pause, complete those ion charges. Come back when you're ready. Okay, so I'm going to write in what I think the ion charges are. 1 plus for potassium. Chlorine, of course, 1 minus. Magnesium, 2 plus. Sulfur, 2 minus. Sodium, 1 plus. Bromine, 1 minus. Oxygen, 2 minus. And calcium, 2 plus. So I'm hoping you will be seeing, if you didn't know it already, that there's a relationship between the group number, the numbers of outer shell electrons, and the charge on the ion formed. Group 1, all the atoms have 1 electron in the outer shell, and they all form 1 plus ions. Group 7 have 7 electrons in their outer shell and form 1 minus ions. Group 2 has 2 electrons in the outer shell, forms a 2 plus. Group 6, 6 electrons in the outer shell, forms a 2 minus ion. So, group number, charge on the ion formed. Can you recall? Fill in the charge on the ion formed for all members of group 1, all members of group 2, all members of group 6, and all members of group 7. Come back to check against my answer when you are ready. Okay, so if I reveal, Every element in group 1 has 1 electron in its outer shell. We'll lose that 1 electron to form a 1+ ion, without exception. Group 2, 2 electrons in the outer shell. We'll lose them both in forming an ion, so all group 2 ions are 2+. Group 6, 6 electrons in the outer shell, gains 2 electrons to form an ion, a stable ion with a noble gas structure, 2- ions in all cases if they're in group 6. Group 7, 7 in their outer shell need to gain 1 electron to achieve a noble gas arrangement, a stable electron arrangement, so all group 7 form 1- ions. Moving on to the structure of ionic compounds. So by structure, we mean arrangement. And ionic compounds form a key word, a giant structure, where the oppositely charged ions alternate. So what does that mean in terms of a diagram? Well, we'd have a positive ion next to a negative, next to a positive, next to a negative. They are alternate positive and negative ions, but not just right to left, also up and down. The attractions between these oppositely charged ions are strong electrostatic attractions, and we call those attractions ionic bonding. But of course, I've put to you a two-dimensional visualization. We also need to think about it in 3 dimensions. So in 3 dimensions, with the ions as solid spheres, we have positive, negative, left to right, alternation, positive, negative, up and down, but also front and back, negative, positive, negative. So we call this a giant ionic lattice. Giant, it never ends. It goes on and on until we run out of ions. Ionic opposites contains ions. Lattice, we have this alternating arrangement of positive and negative ions. Ion-ion attractions are in all directions, as explained. So if we have a negative ion, we'll have positive ions front, back, above, below, left, and right. If we then surround the positive ions with negatives, we build up a cubic arrangement, and this is typical for an ionic compound such as sodium chloride. But we'll also see in textbooks this represented as ball and stick models or diagrams, where we have negative ions surrounded by positives. If we take this positive here, left and right, front and back, above and below, with these sticks representing some of the bonds. If you put in all of the bonds as sticks, then the diagram becomes very confusing. So there's usually just some guideline sticks to provide some shape to the structure. Ionic empirical formula. Ionic compound formulae, such as sodium chloride, are simply written as 1 sodium and 1 chlorine. But if we've got a giant lattice, how is that? Well, the formula represents the simplest whole number ratio of each type of ion. And we call that the empirical formula. So NaCl is an empirical formula. It implies that for every 1 sodium ion, there's 1 chloride ion in the giant lattice. Not that there is a unit of 1 sodium and 1 chloride, but that overall, for every 1 sodium, there is 1 chloride. Those types of formulae are called empirical formulae. Let's look at a structure here, which is magnesium oxide. We've got magnesium and oxygen. If we count up the oxygens, we'll see that we have 14 oxygen ions. And if we count up the magnesiums, we'll see that we've got 13 magnesium ions. The magnesium to oxygen ratio is 13 to 14. Well, bearing in mind we've only drawn a portion of the lattice, the simplest whole number ratio is 1 to 1. So magnesium oxide, like sodium chloride, has an empirical formula of 1 metal ion to 1 non-metal, 1 magnesium to 1 oxygen. It does not mean that we have 1 magnesium and 1 oxygen as a separate unit. It means that if we count all of the ions, look at the ratio between the positive and the negatives, reduce that to the simplest whole number ratio, we then write that as the formula. So here is a problem. We've got an ionic structure or lattice of iron sulfide, sulfur and iron. Work out the empirical formula for iron sulfide. Pause, come back to check your answer when you are ready. Okay, so my count is 14 of iron and 26 of sulfur. Well, the nearest whole number ratio is 1 to 2. Again, bearing in mind that we have only a portion of the structure. So iron once, sulfur twice, FeS2. We can also work out the empirical formula for an ionic compound from the ion charges of each ion in the ionic compound, in the compound formula, because those ion charges should sum to 0, add up to 0. Let's take an example, sodium oxide. Well, we know sodium is in group 1, so it's a +1 ion. Oxygen is in group 2, so it forms the oxide ion at 2-. If we add sodium and oxide together, it does not come to 0. To achieve 0, we need a second sodium ion. So 1 + 1 + 2- comes to 0. So the correct formula for sodium oxide is 2 sodiums and 1 oxygen. Second model, calcium hydroxide, slightly more complicated, only slightly. Calcium is in group 2, it's a 2+ ion. Hydroxide is a group ion, 1-. 1 calcium and 1 hydroxide, we add those ion charges together, they do not sum to 0. So we need a second hydroxide ion to sum to 0. So our formula would be calcium once, hydroxide twice. Now we say we use a bracket here because we need oxygen and hydrogen twice. So to convey the idea that we've got 2 hydroxides, we bracket the oxygen and the hydrogen and then put as subscript 2. The ion charges, of course, can be obtained from the group number in the periodic table, which we covered earlier in this lesson, but just for review. Group 1, all ions are 1+. All ions formed by group 2, 2+. Aluminium, 3+ in group 3. Group 5, we may not have mentioned earlier, form 3- ions. Group 6, oxygen, sulfur, 2-, and of course group 7, chlorine, bromine, iodine, 1-. If you're given a transition metal, assume it's 2+, unless it's silver, in which case it's a 1+ ion. So here are some problems. Sodium iodide, zinc chloride, aluminium oxide, calcium sulfide, silver iodide. Would you like to write the ionic empirical formulae for these compounds? Pause, come back to check against my answers. Okay, so I'm going to go through. Sodium is 1 plus, iodide 1 minus. So we each need one of those. So sodium iodide. Zinc is a transition metal, so we're going to assume it's 2 plus. Chloride is in group 7, so it's 1 minus. So we'll need 2 of those. We'll need 2 chlorides to cancel the 2 positive. Aluminium, 3 plus. Oxygen is 2 minus. So if we multiply 2 times aluminium and 3 times oxygen, that'll come to plus 6 and minus 6. So Al2O3. Calcium is in group 2, so it's a 2 plus ion. Sulfide is in group 6, a 2 minus ion, so it's a simple one. Calcium sulfide. And silver iodide. Silver is the exceptional transition metal. It's just a 1 plus ion. Iodide is in group 7. It's 1 minus. So we need 1 silver and 1 iodide to sum to 0. All these ion combinations sum to 0. 2 plus and 2 times minus 1. 2 times 3 plus and 3 times 2 minus sum to 0. Calcium 2 plus, sulfide 2 minus sum to 0. So that is the key to working out your simple binary ionic compounds. So ionic compounds may involve molecular or group ions. So these refer to ions such as the hydroxide ion, OH, which has a 1 minus charge, the nitrate, the carbonate, the sulfate, the ammonium. So these may be referred to in your specification as molecular ions or as group ions. So the hydroxide, OH, when you see the name hydroxide, it means you've got an oxygen and a hydrogen, overall charge 1 minus. Nitrate is assumed to be 1 nitrogen and 3 oxygens, 1 minus. Carbonate, 1 carbon, 3 oxygens and a 2 minus charge. Sulfate, 1 sulfur, 4 oxygens, 2 minus charge. The ammonium is the only positive molecular ion, NH4, 1 plus. There is no alternative at GCSE to learning these by heart. So hydroxide, OH1 minus, nitrate, NO3 1 minus, carbonate, CO3 2 minus, sulfate, SO4 2 minus, ammonium, NH4 1 plus. So a couple of problems using molecular ions, sodium hydroxide, sodium sulfate, etc. Pause and complete the correct ionic compound formulae. Restart when you are ready to check your answers. Okay, so if you are ready to check your answers, sodium is a 1 plus ion. Hydroxide, you have to know, is OH1 minus. So I need 1 sodium and 1 hydroxide. Sodium hydroxide. Sodium sulfate, sodium remains 1 plus, it's in group 1. You have to recall that sulfate is SO4 2 minus. Therefore, I need 2 sodiums. So I'll write the formula sodium twice sulfate, which is SO4. Aluminium nitrate, aluminium is in group 3. It's a 3 plus ion. Nitrate, you have to recall, is NO3 1 minus. Any variation on that is incorrect. So I need 3 nitrates to cancel the 3 plus on the aluminium, so the ion charges sum to 0. So I need aluminium and then nitrate 3 times. I use a bracket because I'm not just multiplying the oxygen by 3, I'm multiplying the nitrogen by 3 as well. So the bracket tells me that I'm multiplying everything inside the bracket 3 times. Calcium carbonate. Calcium is 2 plus. Carbonate, I have to recall, CO3 2 minus. That's an easy one. 1 calcium and 1 carbonate. The ion charges sum to 0. Ammonium iodide. Ammonium, the positive molecular ion. Iodide is in group 7. It's 1 minus. So we have NH4 ammonium, NH4, and 1 iodide. And finally, the properties of ionic compounds. So let's start with melting points. So we start with a solid in a giant ionic lattice with attractions between oppositely charged ions. And of course, we result in a liquid where the ions are no longer held together in the same way. So they're more distant and the bonds have been broken. So many bonds have been broken. It's a giant ionic lattice with a huge number of ion-ion attractions, opposite ion attractions. And those bonds are strong, which of course means we need a high temperature because large amounts of energy are needed to break the many bonds, all of which are strong. Ionic compounds, with a few exceptions, dissolve in water. So we would write that as an equation, NaCl, for instance, sodium chloride. Action of water gives us a solution, sodium chloride AQ. So here is our solid, our giant ionic lattice with negative and positive ions. The lattice is broken down by the action of water, so the ions are separated by the action of water. An explanation for that would come if you study A-level chemistry. We result in ions that are dissociated. They're spread out amongst the water molecules in a solution, so the ions are now free to move. In the ionic lattice, the solid lattice, they are held in position. In solution, the ions are free to move.
So let's discuss the word electrolyte, which appears in the specification. So here we're going to look at ionic compounds in the molten state and ionic compounds in the dissolved or solution state. And you'll see that, as per my diagram, in the molten state, an ionic compound conducts electricity. I've got a voltage of 8 and a current measured at 2 amps. Similarly, for the ionic compound in solution. So an electrolyte is a substance which, when molten or in solution, conducts electricity, but does not as a solid. So this is the contrast with metals, which conduct electricity as solids. So an electrolyte conducts electricity when molten or in solution, but not as a solid. So my diagrams left and right, molten ionic compound and ionic compound in solution. Now, why would that be the case? Well, let's draw in some ions. So we've got a positive ion and a negative ion, and similarly in solution we've got 3 ions. Pause the lesson and decide to which electrode will the ions move in the process of conduction. Pause, come back when you are ready. Okay, so I'm going to resume. So the positive ions, of course, are attracted to the negative electrode. The negative ions, of course, are attracted to the positive electrode. Opposite charges attract. So positive ions move to the negative electrode. Negative ions move to the positive electrode, the anode. And it's this movement of charged ions that produces the effect of electrical conductance. So if we compare that to a wire, which you will have met in physics, it's electrons that move within wires, such as these wires in the external circuit. So electrons move in the wires, electrons carry the charge and are mobile. But in an electrolyte, it is the movement of charged ions which carry charge.
So you now need to practice. I suggest you first of all do the textbook end of chapter questions, for which you probably can find answers, and then move on to past paper questions from the particular exam board that you are taking. If you don't have immediate access to those, there's a website, Maths and Physics Tutor, which has collections of past papers and answers by exam board.